Hi, how's it going? My name is Carl Diaz. I'm with the Learning Resources Center here at the University of Colorado, Denver. And today we're going to just kind of solve a couple questions here looking at potential energy and objects in simple harmonic motion. So for this first one, we got a box on a spring where that x equals 0 is its equilibrium point. This x equals p is some point in between equilibrium point and max extension, and this x equals a is where it's at max extension or max amplitude. And we're asked some questions. So the first question we're asked is, what is the energy at x equals a? So there we know that there will be no more kinetic energy. All the energy of the system will be converted into the elastic potential energy, which is 1/2 kx squared, where k is going to be the stiffness of the spring or the stiffness of the system, and x is going to be equal to how far we are from displacement. So instead of writing this x squared, I probably should have wrote this a squared. All right. And what is the total energy at x equals 0? Well, once the box comes back there, when it's naturally at rest, the total energy is 0, right? But if this box is oscillating, or imagine this box is oscillating, once it comes from max extension back to equilibrium point, all the potential energy will now be converted into kinetic energy, and this will be actually max velocity. You'll be moving at its max velocity. All the energy will be in terms of its kinetic, and so that's what is all the total energy will be of the system there. All right, what is the total energy at x equals p? Well, at x equals p, we know it's going to have a little bit of potential energy and a little bit of kinetic energy, because at that point, no matter if the box is moving this way or this way, the kinetic, if it's moving this way, the kinetic will be converting into the potential, or if it's moving this way, the potential will be converting into kinetic. So anywhere in between there, it's going to have a little bit of both. So the total energy at x equals p is going to be 1/2 mv squared plus 1/2 kx squared, where again, it's a little bit of kinetic energy and a little bit of potential energy. It's not going to be the potential energy out here because it's not a, it's x, or we could even write that xp, or we could write that p, however you want to write it, right? But that's, right, that x is equal to p there, not that a. All right, so that is just some point. And then v, like we could say 3 meters, they would tell you, x equals p is 3 meters from equilibrium. Okay, so you wouldn't know that. So we would put that in there. You know the stiffness of the spring, you know how fast it was moving, they would tell you, and you could get the total energy, all right? But the idea is that it's a mix between some of the kinetic and some of the potential, all right? And then for the last one, it says, what is the speed at x equals p? Well, like I said, considering from max amplitude, sorry, I forgot that part. Well, all they're really asking us to do is to take part A and part C and put them together, right? Because we know at A, the max energy is just equal to that, right? And we know at P, the energy is equal to this, and so we can use those. And since in terms of conservation of energy, the energy is always equal no matter at any point. So whatever the energy is here is going to be equal to whatever the energy was out here. Or whatever the energy is here is going to be equal to whatever the energy was here. Or whatever the energy is here is going to be equal to whatever the energy is here. The energy of the system, the total energy of the system, right, always stays the same no matter what's going on, right? And so we can use these reference points and this point right here to figure out what we need to. So what we do is since they're wanting us to take from max amplitude, we know at max amplitude it's all kinetic or all potential energy, 1/2 k a squared, and a is just max amplitude, but that would be x, right? And then we know that at point P, the energy is going to be equal to some potential or some kinetic energy plus some potential energy, right? Where that x is a point. Now they would give you in here, like I said, they would tell you like x of P is like 2 meters, so you would know that. All right, you wouldn't have to solve for that. So the first thing we would do is we'd cancel out all those 1/2s, right? There's 1/2 in every term, so those can go away. We're left with just this equation, right? It's just all the 1/2s taken out, and now we can just solve this for velocity, right? And since it's squared, we're going to want to square root everything, but we just divide by m, and v is just left over there, right? And then to get rid of that squared, we want to square root everything over here, so it's going to be this term divided by m, right, where it's k a, where a is the max amplitude squared minus k. X is going to be that 2 meters, that's xp, right, squared, which is that 2 meters over the mass. And they would give you the mass of the object. Let's say the mass is like 10 kilograms, right, and little k is 17. I don't know. I'm throwing some numbers out there. That's pretty much Let's say it's 0.15. Okay, all right. So you know all the numbers in there, and let's say max amplitude was 10 meters. Okay. So if you know all those numbers, you can just solve for velocity, and you will, if you're asked this question, you'll be given these givens. They'll tell you, okay, at 2 meters away from, you know, if the box can extend 10 meters, its full extension is 10 meters, how fast will it be moving 2 meters from equilibrium? That's how this question would be asked. So you would know all those. They would give you the mass and the stiffness of the spring. You'd start with the energy, right, using one of these as your reference point, and then the energy at that particular point, right? And then you'd go ahead and just solve for velocity, right? Okay, hopefully that was straightforward. It's pretty easy, but everything's there. You can rewatch that as much as you need to. Now here, it's a little bit different because we're given this graph where we're just asked to kind of graph what's going on with this box, right? We know that, you know, at equilibrium, it's going to have max kinetic energy. At max displacement or max extension, it's going to have full potential energy. And anywhere in between there, it's going to have a little bit of both, right? We know, right, in this system, we're given the total energy. We say, okay, well, the total energy of the system, right, is 12 joules. So that means the energy of the system always needs to equal 12 joules. That's what that means when we say total energy. No matter where the system's at, right, in terms of its position, no matter where it's at when it's oscillating back and forth, because that's what this is graphing, and I'll explain that in a second. The total energy should always equal 12 joules. That's what this is saying. So the graph, this blue line isn't originally given to you in this question. This blue line is part of C. So what you would originally just be seeing is just that red line. And that red line is the potential energy. So they tell you that that's the potential energy, this red line, okay? And knowing the potential energy of the system, because that's the total potential energy of the system. Maybe you're not using the total potential energy of the system, but that's what that's saying, that the total potential energy of the system can go to 24 joules. But the total energy of the system, how much energy the system actually has, is only 12 joules. So they mark this green line as, hey, this is the total energy of the system, and this blue line isn't there. They ask us to draw in. I say explain the blue line, but what the question asks is to draw in the blue line, or draw in the kinetic energy. Is really what's being asked here, but I'll get to that. Okay, so I just wanted you to understand what's going on. So we have this graph. We know the total energy, which is what the system should always be equal to, no matter if it's at max extension, at equilibrium, or anywhere in between equilibrium, even over here, right? This box is oscillating back and forth. This is its equilibrium point. It's oscillating back and forth. So no matter where it's at, or any object in simple harmonic motion, no matter where it's at, if it has the total amount of energy, it should always equal that, whether it's at equilibrium, max extension, or anywhere in between those points, okay? And this is a graph of that. So what is equilibrium position? Well, we know equilibrium position is where the total energy of the system is just equal to the max kinetic energy. There's no potential energy there, right? So we want to look at, like I said, we originally weren't given that blue line. All we were given is a potential energy line. So we want to look at where the potential energy is equal to 0, which is right here. That's 0 joules, not OJ. That's 0 joules, 12 joules, and 24 joules. Okay, so right here at 5 meters, right, we could see right there at 5 meters, right here, that the potential energy is equal to 0. So we know that equilibrium position is 5 meters because, yes, from that blue line we know it has max kinetic energy, and we'll explain it there. But more importantly, if we didn't have that blue line there, and like I said, originally that blue line isn't given in the question at the beginning, you're asked to draw it, you know this, and that's important. At equilibrium point, you'll have 0 potential energy, and that's where potential energy is 0, so that's how you know where equilibrium is going to be. Where is the mass turning around? Well, we know the mass is going to be turning around when it has max potential energy, right? But we know that the max potential energy of the system that this can have is only 12 joules. Even though this says the potential energy goes up to 24 joules, we know the total energy of the system is only 12 joules. So the potential energy is only going to be, the potential energy is going to max out at 12 joules, even though it has the potential to go to 24 joules. It's only maxing out at 24 joules. That's why they give us that total energy, to know that as a reference. So because of that, we want to look at where potential energy is at 12 joules. Wherever potential energy is at 12 joules, that's where it's going to be turning around, because the system, all the potential energy will be or all the system's energy will be converted into the potential energy, and it should all equal 12 joules, because that's what the total energy of the system should always equal. So we know at that point there should be zero kinetic energy, right? And we don't have that blue line yet, but that's what that blue line's explaining. But we know that the potential energy, right, is going to, the 12 joules is the max energy that the potential energy can have here, because that's what this question told us. It told us 12 joules is the total energy, so that's all the maximum potential energy it can have, even though it goes up here, okay? So wherever that is, that's where we know it's going to stop and turn around, because that will be the max potential energy of the system. So at 2 and 8, we can see that. So we say at 2 and 8, right, because the system has max potential energy based off the total energy we were given, we know that that's where it's going to be turning around. Now, they go ahead and say, now draw on the kinetic energy. And so what you would do is you would say, okay, well, I know it's turning around at 2 and 8. So the kinetic energy better be 0 at those points. So that's where you want to start this line, either there or there, and say the kinetic energy needs to be 0 at 2 and 8, because I know that's where the mass is turning around, and where the mass turns around, it has max potential energy when it gets out here, right? That's what we're saying. And we also know at equilibrium, which we've said we know where equilibrium is because potential energy is 0 there, kinetic energy should be max, right? So when we make this graph of the kinetic energy onto this potential energy graph, we know we want to start it at 2 meters, we want it to peak at 5 meters, and then we want to end it at 8 meters. Again, why? Because we know at 2 and 8 meters, the potential energy needs to be max, right? And there shouldn't be any kinetic energy, and since the total energy is 12 joules, that's where potential energy would be 12 joules, and where we would have 0 kinetic energy. And how do we know? We just said it. This blue line's saying that 0 joules. If the blue line, right, blue line is the kinetic energy, right, then we know it's 0 at 2 and 8, which that's the turnaround point, which we said, and it's max at 5, which again should be equilibrium. So that's how we know how to draw that, okay? Now again, you might see graphs that start over here and they go over here and they max out at the top of potential energy. Well, if the max energy was the same as the max potential energy of the system, then you would draw the kinetic energy that big, but they told us the total energy is only here. So when the potential energy equals 0, we know all that's left is kinetic energy. The system still needs to be equal to 12 joules there. So the kinetic energy needs to stop there. It can't go up here. It can't be at 24 joules, because that's exceeding the amount of energy that the system is going to make. It only maxes out at 12 joules, okay? So that's where the kinetic energy needs to also max out at, okay? So the potential energy, even though it says it comes up to here, is maxing out right here and right here, which is why we know those are our turnaround points. And the kinetic energy is maxing out right here, again, because we know that's equilibrium, but all because we know that's the max energy of the system, and no matter where we're at, so anywhere in between here, the numbers, as they see as one goes up, the other goes down, as those numbers change, it still equals 12 joules, 12 joules, 12 joules, 12 joules, 12 joules, 12 joules, okay? It's important to know that. All right, I hope this was helpful. Again, go back and watch these if you need to. They're explaining not just simple harmonic motion, but potential energy and kinetic energy as well, associated with like an elastic system. All right, I'll see you on the next video.